Welcome to Lecture 13 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, we will begin our study of the firm's costs. And in this lecture, we'll focus on short-run costs. That is, costs derived using the short-run production function. So lots to cover today, so let's get started. The firm's objective in microeconomics is to maximize profits, and we know already that profit is revenue, the money that the firm makes, minus the firm's costs. So in order to maximize profits, or even to understand its profits, the firm needs to understand its costs. In this lecture, we're going to use the mathematical device called a total cost function. We'll denote this capital C, and it depends on output Q. So what this tells us, C of Q tells us the cost required in order to produce that output Q. Now, you could always incur more cost. You could simply set fire to a pile of money and still produce the same output Q. So C of Q tells us not only the cost required to produce an output Q, but more specifically, it's the minimum total cost required in order to produce that particular level of output. Now, we might expect that as a firm tries to produce more output, that it's going to cost more. So we would think of this cost function as being an increasing function, for example. This might not always be the case, but would be a reasonable assumption, at least in some regions of output. Now, we can distinguish between what we call variable costs and fixed costs. So, for instance, if I need to employ more units of labour and pay each of those units of labour a wage in order to produce more output, then labour is treated as a variable cost. It's telling us the part of the total cost that is varying as I try to produce more output. Fixed costs, on the other hand, do not vary with output. So one way of thinking about fixed costs is to say, well, what's the cost of producing zero? Okay, so even if the firm don't produce anything, maybe I still need to pay a particular rent on my property. I still need to pay many other overhead costs. So, and since these do not vary as I try to increase my output, we call them fixed costs. So as a basic identity, we think of the total cost function C of Q being the sum of two parts. Firstly, the variable cost, which depends on output, plus some fixed cost, capital F, which does not depend on output. Now, sometimes we'll think of fixed costs as being sunk. Now, a sunk cost is a cost that, well, there's various definitions, but for us here, it means that it's unavoidable, at least in the short run. Okay, so it's a cost that I cannot escape. Now, in the long run, you may be able to escape this cost. So if, for instance, we're thinking of the fixed cost for the firm of being the cost of having the property or the building where it's going to produce output. Now, in the short run, perhaps it can't change that. So the fixed cost, we would consider that a sunk cost in the short run. And effectively, because we can't change it, it could be ignored in our profit calculations. You'll see this when you study firms operating in competitive markets, where essentially the firm's break-even decision is either going to look at costs in the long run, or in the short run, it's just going to focus on variable costs because the firm chooses to ignore fixed costs in the short run. We won't make this distinction too much today, however. Once the firm knows its cost function, its total cost function, there are various cost functions that we're going to derive from this that will be useful for the firm's analysis and the firm's decision making. The first of these is the concept of marginal cost. Now, the definition of marginal cost is essentially the cost of producing an additional unit of output. Now, we're going to think of output as being a perfectly divisible, continuous variable. So when we say marginal cost, we'll think of the first derivative of the cost function with respect to output. So if we increase output a little, how does our cost change? This is what we mean by marginal cost. Marginal cost is absolutely central when the firm is trying to decide the level of output in order to maximize profit. To give you the idea, if we were going to maximize profit, we would differentiate a profit function with respect to output. So we would have differentiate revenue, which would give us something called marginal revenue, and differentiate cost, which would be marginal cost. And finding the output that makes marginal revenue equal to marginal cost is precisely the necessary condition for maximizing profit. There are some second-order conditions to verify, but that's the first-order condition, is going to use this idea of marginal cost. What does it mean graphically? Well, if we were to sketch the firm's cost function as a function of output, so in this diagram I've drawn output on the horizontal axis and cost on the vertical axis, and this blue curve is a typical cost function. I've drawn it increasing and convex in this case. This is a very common assumption, but not all cost functions will look like this. In this case, the marginal cost at a particular point, so MCQ, would be the slope of this red line, which is tangent to the cost function at that particular value of output Q. Marginal cost is the first important thing that a firm needs to know in order to decide how to produce, so to decide its profit maximizing level of output. A second key idea that the firm will need to know is what's called average cost. So we'll think of an average cost function as follows: average cost, capital AC, as a function of output Q, takes the total cost function C of Q and then divides by the level of output Q. This, in a sense, gives us the average cost per unit of output. Now, the firm will use this when deciding whether or not it is breaking even. So that if the firm wants to maximize profits, it will determine a particular level of output. It may be the case that this maximum level of profit is not even positive. Okay, so the firm would be losing money by producing even at its very best level. So it's important to know, well, what level of output is required in order to actually make some profit. And for this, we just need revenue to be greater than cost. Okay? Now, if we think of revenue as price times quantity, and then we divide by quantity, so we're just looking at the price and comparing it to average cost. Okay, so if price is greater than average cost, then the firm is making positive profit, so it stays in business. It can then think about maximizing profit, knowing that profit is positive. Of course, this is where we would distinguish between the short run and the long run. You'll see this next semester, or if you have a look forward at chapter 8 in the textbook, where the firm either compares the price with average total cost in the long run, or in the short run, it simply compares the price with the average variable cost, treating fixed cost as sunk. Okay, so knowledge of the marginal cost function is crucial for finding profit maximizing output. Knowledge of the average total cost function is crucial for knowing when a certain level of output is going to actually generate enough profit to be a non-negative amount of profit. So how would we interpret this idea of average cost graphically? Well, here I've produced the graph of the same total cost function again. So I've drawn an increasing and convex function C, which is the light blue curve. And if I want to calculate the average cost of any particular level of output. Here I've chosen a level of output Q. I connect a purple line or pink line from C of Q back to the origin, and the slope of that line, which is the height CQ divided by the length or the width, which is Q, tells me the average cost. So the slope of that pink line tells us the average cost. If I looked at the slope of a line tangent to the cost function at that point, it would tell me the marginal cost. Similarly, we can use this idea of average cost to distinguish between average fixed cost. So remember that total cost, C of Q, is equal to variable cost plus fixed cost. So in the same way, average cost would be equal to average variable cost plus average fixed cost. What do we mean by these definitions? Well, average fixed cost, which is defined for Q greater than 0, just because we can't divide by 0. Average fixed cost would be simply the fixed cost divided by Q. Notice that average fixed cost is always decreasing. The more we produce, average fixed cost is always coming down. For very low levels of output, average fixed cost is going to be quite high. Average variable cost takes the variable cost function VCQ and divides it by the level of output Q. And of course, average total cost is the sum of average variable cost and average fixed cost. So now that we know the basic definitions of these various types of cost functions, let's just work on a graphical example and suppose that we're given a total cost function that looks like the following. C of Q is equal to 100 times Q minus 4Q squared plus 0.2 times Q cubed plus 450. So we're given a cubic cost function. In this case, it's not always increasing in this case, but it's a relatively typical example of a cost function. And then the exercise would be, well, use the definitions that you've been given of average variable cost, average fixed cost, average cost, and marginal cost. Use those definitions to produce a set of reasonably accurate diagrams of all of these different cost functions. So I would encourage you now to stop the tape and pause and have a go at this exercise. We're going to approach it in a similar way than we did in lecture 11, where we looked at short-run production function. So just use calculus and any other trick you can throw at this to find out as many facts as you can about each of these functions and how they relate to each other in order to produce a reasonably accurate set of diagrams. So we'll do that in a second on paper, but first have a go yourself. Okay, so let's have a look at this problem we've been given. We've been given a cost function. C of Q is equal to 100Q minus 4Q squared plus 0.2 Q cubed plus 450. Okay, and we want to produce diagrams of, well, the cost function itself, of the marginal cost, and various average cost functions. So average variable cost, average fixed cost, and average total cost. Okay. So I'm going to approach this in a similar way that we did in the short-run production lecture, where I'm basically going to gather as many facts as I can, firstly about the general shape of each of these particular functions. But I also, as I'm drawing a diagram, I'm going to draw the marginals and these various average cost functions on the same diagram. So it's important to get the functions placed correct relative to each other. Even if we're not drawing them absolutely correct, we want the relationships between these functions to be expressed correctly. So where do they intersect, and so on. Okay, so let's start by looking at marginal cost. So the marginal cost, we know the definition is the first derivative of the total cost function. So if I take that derivative, I get 100 minus 8q plus 0.6q squared. Okay, so that's the marginal cost function. So let's make some notes over here about what it looks like. Well, it's got this plus q squared here, so I know it's a convex quadratic. Okay, so it's going to start decreasing, reach a minimum, and then increase. Okay, that's what it looks like. I could also read that the marginal cost at 0, so if I'm producing 0, the marginal cost is just 100, so that's where this curve intercepts the vertical axis. What about where it's minimized? So I said it's going to come down, decrease to some point, and then after that level of output, it will increase afterwards. So it would be good to know that level of output. So where does that minimum of marginal cost occur? Well, to find that, all I need to do is differentiate this and then find the value of q that makes that derivative 0. So let's take the derivative of the marginal cost function. The second derivative of the cost function would be minus 8 plus 1.2 times q. Okay, that's the first derivative of marginal cost, or the second derivative of the cost function. We're looking for the q star that makes that 0. Okay, and that's the same as q star being equal to 8 divided by 1.2, which is 6.67. Okay, so put MC min. MC is minimized at q equal to 6.67. Okay, and we could actually calculate the value at that point. We could say, well, what is the value of marginal cost at 6.67? So I just take that, plug it into 100 minus 8 times 6.67 plus 0.6 times 6.67 squared. And when I did that, I got 73.3 to 1 decimal place. Okay, so that should be enough information to get a pretty decent sketch of this marginal cost function so far. Okay, let's have a look at average variable cost. Well, we know average variable cost is variable cost divided by q. It's defined for q greater than 0. It's not really defined at 0. Although in this case, our curve, we can write down where the curve approaches at 0. So what's the variable cost? Well, if I look at the expression 100q minus 4q squared plus 0.2q cubed, clearly each of these three terms depends on q, output, but this fourth term, the 450, it doesn't depend on output. So I'll say that the 450 is my fixed cost. Okay? Essentially the cost of producing 0. If I try to produce 0, I still have to pay the fixed cost, and that's 450. And it remains there no matter how much more I decide to produce. What about, so the variable cost is these other three terms. So let's divide them by q. So the average variable cost would be 100 minus 4 times q, q squared divided by q is q, plus 0.2 q squared. Okay. So what do I know about this? Let's write down some facts. Again, in this case, it's a convex quadratic. I know that this, we could write AVC goes to 100 as q approaches 0. Okay, so strictly speaking, we said the average cost functions are not defined at 0, but we know that if q gets close to 0, this is getting close to 100. Okay, what about its minimum value? It's a convex quadratic. When it intercepts the vertical axis, it's close to 100, and then it comes down and then increases again. So where does that minimum occur? So if I differentiate this, I will get minus 4 plus 0.4q. That's the first derivative of the average variable cost function. And I'm looking for the particular q star that makes that 0. Okay, so q star would be 10. 4 divided by 0.4. Okay, so AVC min at q equal to 10. So what is the average variable cost at that point? Average variable cost at 10 is equal to 80. I could just plug 10 in back into here. 100 minus 4 times 10 plus 0.2 times 10 squared. Okay, and I get 80. Okay, so I've got two curves. What about where do they cross? Okay, so one way to do this, I could set marginal cost equal to average variable cost as an equation and then solve for the q that makes that true. Okay, so that's not too difficult to do. But I'll just give you the answer at this point. This is also equal to the marginal cost at 10. Okay, so average variable cost where average cost is minimized, so 80 is the lowest value average variable cost takes, turns out to be precisely where marginal cost equals average variable cost. So we'll prove that later in the lecture. But for now, you could have figured that out numerically, but it's part of a very general fact. Okay, so we know how to draw both of these curves and we know how to place them correctly relative to each other now. What about some of the other curves? So average fixed cost would be the fixed cost 450 divided by output Q, as long as output's bigger than 0. Okay. Now to draw something like this, you could use calculus. You could differentiate once and you'll find it's a negative, so it's a decreasing in Q. And if you differentiate again, you'll get a positive, so it's decreasing and convex. But you could think about this in terms of asymptotically. So think about as Q becomes incredibly small, so dividing by 0.001 is the same as multiplying by 1,000. Dividing by 0.00001 is the same as multiplying by 10,000, if I said the right amount of zeros. But you can see as Q gets very close to 0, this term is going to explode. Okay, it will be enormous. Okay, so its average fixed cost for very low values of Q is going to be incredibly high. As Q becomes enormous, however, so if we look at Q becoming very large, divide by 1,000, divide by 2,000, 450 divided by 10,000, divided by 1,000,000, and so on, this thing is getting closer and closer to 0, okay? So it's going to start incredibly high, and then it's going to come down in a convex, decreasing way and get closer and closer and closer to the horizontal axis. Okay, so that's enough to help us draw it. We could always pick out some value to place correctly, so we might do that. Okay, and then the final one, average cost, would be average variable cost plus average fixed cost. Okay. Now, to produce a diagram of this is kind of the trickiest. You could write out the expression, the parametric form for this, and then use some facts of calculus to figure out what it looks like. But I'm going to just focus on this term to give you the idea. So we said if Q is very small, this average fixed cost, so if Q is close to 0, 0.000 something, this term is enormous. Okay, so average cost is going to be enormous for very low levels of output. If, however, Q is very, very high, so if Q is 1,000, 2,000, 1,000,000, then this average fixed cost term is going to disappear, and the average cost is going to get closer and closer to average variable cost. Okay, so that helps us draw this. Average cost will start incredibly high for low levels of output. It will come down in a convex way, and then it's going to get closer and closer and closer to the average variable cost curve. Okay. Now, you could also solve analytically that this average cost curve is minimized when Q is equal to 15. So there's two ways of doing that. What I did was I wrote down the average cost, differentiated it, and I ended up with a cubic equation, which I then solved using a computer. But you could solve it by paper, but I didn't. I used a computer to find this. But it just so happens that this is precisely where average cost is equal to marginal cost. Okay. Which is a similar thing with this average variable cost. So where this average cost is minimized, it coincides with the marginal cost curve. That's something we'll prove more generally after we've done this exercise. So that will be next in the lecture. Okay. Okay, so now we've got enough information. Let's actually start putting this together onto some diagrams. So let's start. I've prepared, if I cover this working area here, prepared this diagram here with output on the horizontal axis and cost on the vertical axis. Okay, now let's place some of our values. What did we have? We had 100 was important, 6.67, 10, 15. I'm not placing these perfectly accurately to scale, but we want to draw these diagrams correct relative to each other. Okay, and where was marginal cost? Minimized at 73, so let's put that there. 73.3, and average variable cost is minimized at 80, so let's put that there. Okay. Right, so the marginal cost curve is a convex quadratic. It starts at 100 at its lowest point here. It's minimized when output is 6.67, in which case it gives a value 73.3. And then after that, it increases ever after. Okay, so let's draw that. So it's a convex shape. So it's decreasing and convex up to this point. And then afterwards, it's going to increase something like this. Let's keep drawing it. Marginal cost. Okay. So that's a reasonably accurate drawing of our marginal cost curve. Now let's place the average variable cost. Where would this go? We know that it starts close to 100 and that it's minimized when Q is 10. And also that that's where it intercepts this marginal cost curve. Okay, so I'll make that blob a bit larger to correct my drawing. So this should be 80 here. Okay. So it's going to come down to this point here and then start increasing afterwards. Okay. So it should come down smoothly, reach the minimum value at 80 and where output is 10 and then start increasing afterwards. So that's our average variable cost curve. What about the average total cost? So average total cost, we said that when output is 15, it coincides with this marginal cost. Okay. And then we had two other facts. So this is where average cost is minimized. It's going to increase after this, but it's going to get closer and closer to average variable cost. So it's increasing and getting closer to that average variable cost. That's average cost. Average cost. But here it was increasing and then it becomes enormous as output becomes very small. Okay. So this decrease starts off enormous, average cost, average total cost, decreases until it just touches the marginal cost curve. Then it starts increasing and getting closer and closer to the average variable cost curve. And it gets never quite touching it. Okay, but it's going to get closer and closer asymptotically. Okay, so we've drawn the marginal cost, average variable cost, average total cost. What about this average fixed cost? Well, it's going to start incredibly high and then it's going to get very close to the horizontal axis as output becomes very large. Now we could put some values in just to help place it correctly. So for instance, the average fixed cost of 10, 450 divided by 10 is 45. So this point here was 80. So let's pop a point there and say that's 45. Okay. Then the average fixed cost is going to come, it's going to get incredibly large as Q is very small. It's coming down and down, and then it's going to get closer and closer to this axis. Okay. Apologies for the scruffy drawing there, but you can see the kind of general shape, and it's placed correctly relative to the other curves in this diagram. Okay. So that's the marginal cost, average variable cost, and average fixed cost. So now let's have a look at the total cost function. Okay, I'll draw this on a separate diagram. So let's just mark in our points. We said 6.67 was interesting. Something interesting happened at 10 and something interesting happened at 15. Okay, so they might be useful. So at 15 was where, when output is 15, average cost is minimized. Okay, so if I'm drawing a cost function, remember that average cost was, if I connect a point on the cost function with the origin and look at the slope of that line, then that's how we can find the average cost from the cost function, or the reverse as we're doing here. So let's start with 450, our fixed cost. We could just draw that. We could draw the fixed cost function. We weren't asked to, but it's so easy for free. Fixed cost. Okay. So now what do we know about the cost function? Well, marginal cost is the slope of the cost function. Okay. Now it's positive here. It starts off at 100, it comes down to 73, and then it starts going up again. Okay, so this is an increasing function, but we know that it's minimized. So marginal cost is decreasing up to this point. Okay, and then it increases after that point. Okay, so it starts off being concave, marginal cost decreasing, and then switches to being convex. Okay. Now we also know that if I could draw this accurately, which is not so easy, let's just draw a line like this and say that this, if you can see that line, that this point here, let's say that this line has slope of the average cost evaluated at 15, okay, which is, I have the number 115, okay? So that's the minimum average cost. So if I'm connecting the cost function back to the origin with a line, this is it always has to be above this line, okay? So that's going to help us as well. It's also where it's precisely equal to the slope. Marginal cost equals average cost at this point. So this is actually a tangency. Okay, so there's a tangency here. If I just draw very lightly a tangency, I know it's going to start off by increasing and concave. Okay, then it's going to switch to increasing and convex at this point. Okay, so if I try to incorporate all of that, I'll start with pencil. So increasing and concave up to this point, where it switches to increasing and convex, and then tangent here. Okay, so it's not too easy to draw, but we've got the basic facts down. Increasing and concave, switch to increasing and convex. It's getting steeper and steeper and steeper. That tangency there, it's getting steeper. Okay, so there's a reasonably accurate drawing of the total cost function. Okay, now given that we've got the cost function and you've got the fixed cost there, it wouldn't be too much of a challenge to draw the average, to draw the variable cost function as well by shifting this down, and you could use the average variable cost to determine the slope at a particular point. Okay, so that was a rather involved exercise, but we did come across something interesting, that these where these curves are minimized, that average cost is equal to marginal cost where average cost is minimized, and average variable cost is equal to marginal cost where average variable cost is minimized. So that's what we will now have a look at proving more formally next. So while we were drawing the diagram in the previous example, these diagrams of cost functions, we came across the property that marginal cost is equal to average cost where average cost is minimized. And a similar condition holds for average variable cost. Marginal cost and average variable cost are equal when average variable cost is minimized. So let's prove this formally now. So we're going to prove that marginal cost is equal to average cost when average cost is minimized. Okay, so this is very similar to our work on marginal product of labor and average product of labor. So let's just take the definition. The average variable cost calculated at a point Q, ACQ, is equal to the total cost, C of Q, divided by Q. Okay? So let's minimize this function. So how do we minimize? We find the derivative, we differentiate once, and then we find the particular value of Q that makes that derivative equal to 0. So if I take the derivative of this average cost function with respect to output, okay, now I'm going to use the quotient rule. So if you can't remember this, have a look at lecture 11. But the quotient rule says if I want to differentiate, so here we have C of Q, so one function of Q divided by another function of Q, the identity function, Q equals Q. So if I want to find the derivative, I use the quotient rule as follows. So I differentiate the top function, marginal cost of Q, multiply it by the function on the bottom, Q. Then I differentiate the bottom, which will just be equal to 1, and multiply it by the cost of Q. And then I divide everything by the bottom function squared, so Q squared. Okay? So this is just using the quotient rule from calculus to differentiate the average cost function. Okay, now if I just take one of these Q's outside of a bracket, I end up with marginal cost of Q multiplied by Q and divided by Q again. So that's just marginal cost of Q minus the cost of Q divided by Q once and again. So divided by Q. Okay? And we can see that this is equal to 1 divided by Q, the marginal cost of Q. And here I've got total cost divided by output, which is average cost of Q. Okay? So that's a general expression for the derivative of the average cost function with respect to output. Now, if this is going to equal 0, then what we need is that this term in the brackets here equals 0. And that only happens if marginal cost is precisely equal to average cost. Okay, so at the point where we're minimizing the average cost function, at that particular level of output, the average cost of that output and the marginal cost of that output are equal to each other. So far, in this lecture and in the previous 2 lectures, we've treated production and costs as separate topics. Really, this couldn't be further from the truth. Production and costs are intimately connected. So let's have a look at the relationship now. To see this, let's consider a short-run production function where output Q is equal to a function g of labour L. Okay, now I've derived this function g by taking a long-run production function f, which depends on L and K, and I've taken capital K as fixed at some level, K bar. In which case we have that output is only changing as labour changes. So Q is a function which we'll call G of L. If G is an increasing function, then I'm able to invert it. So there exists a function which we call G to the minus 1, which if I plug in a level of output Q, so I take G to the minus 1 and plug in the output level Q, out pops the amount of labour L. So what does this mean? Well, it's saying if I know I want to produce Q, if I plug it into this function G to the minus 1, the amount of labour L that pops out is precisely the amount of labour I need in order to produce exactly Q units of output. Okay. Now let's consider the costs, the short-run costs. So if we have a fixed given wage rate W for labour, this is a very common assumption related to competitive markets. So we can't change the wage rate. Nobody has market power. We just take a wage rate as given as W. Then our variable cost of producing an output Q will be equal to W times L. Okay. But which L in particular? Well, it's the specific L that is required in order to produce an output level Q. So really we have WL is equal to W multiplied by the function G to the minus 1 evaluated at output level Q. Okay, so using these two basic assumptions, if I know the short-run production function and I know the price of labour, the wage rate W, then using those two assumptions together, I can derive the firm's variable cost function. Similarly, the total cost function will be the variable cost function plus some fixed amount. This might not appear in the short-run production function, but we've already gleaned a lot of information just from the short-run production function. And indeed, if I look at marginal cost, where the fixed cost part does not change with Q, then I would be able to evaluate marginal cost just using the short-run production function and this wage rate. Let's do an example on paper now where we use a specific parametric form, our familiar Cobb-Douglas short-run production function. Okay, so let's have a look at deriving cost functions when we're given a short-run production function. So we're going to work with the short-run Cobb-Douglas production function as the simplest example. So Q is equal to gamma times L to the power alpha, okay, where gamma and alpha are greater than 0. When we saw the long-run Cobb-Douglas function, we had Q is equal to A times L to the power alpha times K to the power beta. Now in the short run, we're going to take capital as fixed, and A was fixed, and beta is fixed. They're just parameters. So they are all consumed by this constant gamma here. And we're just writing Q equal to gamma times L to the power alpha, okay? Now, if I invert this function, if I write L as a function of Q is equal to, and then invert this, so I would have Q divided by gamma to the power 1 over alpha, okay? So what does this tell me? It's the... what it means, let's call this the labour required. So the idea is if I know how much output I want to produce Q, I could plug it into this function, L of Q, and out pops the number of units of labour that I need to employ in order to produce Q. Okay? I don't think it has a specific name, but we'll just refer to it as the labour required for output Q. Okay, so our first assumption is that we know the short-run production function, and our second assumption will be that we are given a wage rate W. Okay, so wage W is just the price of a unit of labor. We're assuming some kind of competitive market here for labor, by which I mean this wage rate is just fixed. Nobody can change it. Nobody has any market power. Every unit of labor costs exactly the same. We pay each of them a flat wage W. Okay, so that's a simple assumption. What can we say then? Well, now, suppose I want to talk about the variable cost of output Q. Okay, now capital is fixed, so the cost of capital isn't going to come into this, but labor is my variable, so I'd be taking W and multiplying it by L. Okay, that would be the variable cost associated with output level Q. But which L am I using here? Okay, so what I mean is, well, it's the specific L that is just enough labor in order to actually produce an output Q. And we denoted this L of Q. Okay, so I could write the variable cost of Q is equal to W multiplied by Q over gamma to the power 1 over alpha. Okay, so now I have, starting from a short-run production function and assuming the wage rate is given and fixed, I could now immediately derive the variable cost function. Okay, I could derive the cost function almost as the variable cost W of Q divided by gamma to the power 1 over alpha. Just it will be adding some fixed cost. Okay, so we might not be able to read off what the fixed cost is here, but we've got most of the information we would need about the total cost function. Okay, in particular, we can calculate the marginal cost of this. So the marginal cost of output Q, of course, fixed cost won't enter into this. So we could differentiate this expression here. So let's differentiate this. So we could use the chain rule here and write W over alpha Q to the power gamma to the power 1 over alpha minus 1, and then differentiate inside the bracket. Inside the bracket would be 1 over gamma. Okay, so there's our marginal cost function. Could do with some tidying up. Now, tidying up is not strictly necessary, but it's good practice. So we've got 1 over gamma here to the power 1 over alpha minus 1, and then plus 1. So that would just be 1 over alpha. And then Q we've got to the power 1 over alpha minus 1. But a neater way of writing that is 1 minus alpha over alpha. It's exactly the same, but it looks a little neater. Okay, so that's the marginal cost function, and the average variable cost function again would be the variable cost divided by Q. So we would have W times Q over gamma to the power 1 minus alpha, and then divide by Q. So multiply by Q to the power minus 1. Okay, would be another way of writing that. And this would be W 1 over gamma to the power 1 over alpha multiplied by Q to the power 1 minus alpha over alpha. Okay, so marginal cost and average variable cost here, the only difference is this 1 divided by alpha term. But yes, so we get a lot of mileage just by gaining knowledge of our short-run production function and knowing the market wage rate. We've been able to derive all of the short-run cost schedules precisely. Let's consider another simple way of relating productivity and costs. So let's recall the definition of average variable cost, which is variable cost of output Q divided by output Q. And if if we have a wage rate and we're only employing labour, variable cost is equal to W times L. So average variable cost is equal to W times L divided by Q. Now recall average product of labour. The definition of average product of labour was the number of units of output we're producing divided by how many units of labour it takes to produce that output, L. Here in the average variable cost term, we see L divided by Q, which is the average product of labour, but upside down. That is, average variable cost of output is precisely equal to the wage rate W divided by the average product of labour. This means average variable cost is inversely related to average product of labour. This is an incredibly useful thing to know. For example, knowing that average variable cost is inversely related to average product of labour means if I know average variable cost is decreasing, then I know average product of labour is increasing, and vice versa. If I know average variable cost is increasing, then I know average product of labour is decreasing, and vice versa. Also, I could say if average variable cost is minimized at a particular output level Q star, then because average variable cost is inversely related to average product of labour, I know that average product of labour is maximized at that same level of output Q star. So simply knowing that these are inversely related allows me to gain lots of quick facts about these different short-run production and short-run cost functions. A similar relationship exists between marginal cost of output and marginal product of labour. So recall that marginal cost of output is the first derivative of the cost function, the total cost function, with respect to output. Now, if I'm differentiating the total cost function, this is the same as differentiating the variable cost function because the derivative of the fixed cost will simply be zero. Okay, so differentiating the variable cost, which is W times L, I would get W times the derivative of L with respect to Q. Okay. Now recall the definition of marginal product of labour, which is the derivative of output with respect to labour. How does output increase as I increase my labour by a small amount? Now looking at these two equations, in the marginal cost expression, we have dL over dQ, and in the marginal product of labour expression, we have dQ over dL. So in the marginal cost expression, we have the marginal product of labour inverted. So we have marginal cost of output is equal to W, the wage rate, divided by the marginal product of labour. Marginal cost is therefore inversely related to marginal product of labour. Again, I can come up with some quick deductions using this knowledge. If I know, for instance, that marginal cost is decreasing, then I know that marginal product of labour is increasing. If I know that marginal cost is increasing, then I know that marginal product of labour is decreasing. Indeed, this is a very common assumption. Decreasing marginal product of labour or diminishing marginal returns is frequently assumed, and increasing marginal cost, which is implied by the former, is what guarantees that your second-order conditions for profit maximisation are met. So that will be an important case as you study markets next semester. I could also say if marginal cost is minimised at Q star, then marginal product of labour is maximised at Q star. So these are just some of the examples, the quick deductions you can make once you know that two functions are inversely related. So that concludes our study of the firm's costs in the short run. And what made today's lecture quite simple was the fact that we were working with the short-run production function when we were trying to derive the firm's cost functions. In particular, what made this simple was the fact that, given that we assumed capital was fixed at a certain level, when we wanted to produce a certain amount of output Q, there was only one appropriate quantity of labour that would do the job in order to produce this level of output Q, and so we could take the cost of this particular level of quantity of labour required and take that as the firm's variable cost. So this is very simple. In the next lecture, when we look at the long-run case, it gets more complicated because for any target level of output, there are many different combinations of labour and capital that would all do the same job. That is, they would all produce the same level of output. We've seen this before. It would be all of the different combinations of labour and capital along a particular isoquant. How do we calculate the cost then? Well, we're going to have to optimize our choice of labour and capital, choose the right combination. Hence, in the next lecture, we'll study what's called the firm's cost minimization problem. And from this, we'll be able to derive the long-run total cost function and all the associated cost functions for the long-run case. So, lots to look forward to in our final lecture, but in the meantime, take care.